Hello everyone. So in this session we will be discussing about parallel processing. In parallel processing, we are just going to discuss about multiple processor organization. Before getting into this topic of parallel processing, we will just see why there is a need for parallel processing. See, already we know the CPU will have its own phase of execution. If I want to improve the performance of the CPU, there are different techniques available, and one such important technique is called parallel processing. As the name implies, if the CPU is able to process things in parallel more than one at a time, then obviously the throughput that could be achieved from the CPU could be improved. So, to improve the performance of the CPU, the important technique to be followed is parallel processing. And to do parallel computing, what is the basic infrastructure requirement, or in what way the CPU is able to improve its performance, that will be discussed under this topic, multiple processor organization. Here, we can do parallel computing either with a single processor or with a multiple processor. Obviously, there could be a question, if it is a single processor, how it can perform more than one at a time. So even if it is going to be a single processor, if there are multiple functional units, so these functional units can be activated and they might be allowed to do their operations in parallel. Thereby, even with single processor itself, we will be able to do some parallel processing. So in general, parallel computing demands some infrastructure either at the functional units level or at the processor level. So actually in parallel computing we are going to take the jobs, and the jobs are job, what actually we mean by job is the input problem what we are going to find the solution, and they are broken into discrete parts. Okay, so why we mean by discrete parts? So it has to be divided into independent units so that they can be executed in parallel. If there is a dependency between one unit and another unit, then obviously parallel computing will be restricted or limited. So it is further, once you have divided into discrete parts, then it is identified as a series of instructions, and these instructions are going to be executed simultaneously in different CPUs. We will be having different processing units. So that's it. Here we are going to focus on multiple processor organization. If there are multiple processors available, the given problem is divided into subunits, and these subunits are going to be submitted to individual processor. The parallel system deals with simultaneous use of multiple computer resources, okay, which may include a single computer with multiple processors or number of computers connected by the network. Here, one important point what you have to remember is parallel processing can be done only with multiple in multiple units. This multiple units can be at different levels. Okay, if we have only single CPU, then we can have multiple functional units. Okay, if we have multiple processor, then each processor will have their own functional units which can do things in parallel, or it can be even multiple computer. So multiple processor in a single computer can be there, or even you can go for multiple computers. If it is going to be multiple computers, then we are going to connect all these computers together to form a network, and the given problem will be distributed across the computers in that network. So by parallel computing, we mean that we demand multiple infrastructure. So the multiple infrastructure can be at different levels. At starting at the lowermost level, it can be a functional unit, multiple functional unit, or it can be multiple processor in a single computer, or it can be multiple computers itself. If it is multiple computer, all these computers are to be connected together as a network so that we can distribute the problem across the different network. So parallel computing can be achieved at different infrastructure level. So that's what we have discussed. So parallel systems are more difficult to program. Why they are more difficult to program? If it is a single processor, we will be scheduling that single processor with different process. If it is going to be multiple processor, then that should be proper coordination among the processor. So coordinating activities has to be planned properly. We have to schedule the entire job across multiple processes in a proper manner, such a way that we have to identify independent units. If one is dependent on another, then parallel computing may not be that much feasible. So the crux of parallel processing is going to depend on the CPUs. Okay, so based on the number of instructions it is going to execute, and based on the number of data it is going to operate, we can have classification of this parallel computing systems. Actually, there is a famous scientist by the name Flynn. So he has introduced different classifications of parallel computing models. Okay, so that is otherwise called as Flynn's classification. So if you just observe this diagram, we are just going to classify that based on two important terminologies. One is called as the instruction stream, another one is called as a data stream. Okay, so what is this instruction stream? If the CPU is able to execute more than one instruction at a time, then it comes under the category one or many. Similarly, at any given point of time, the CPU may be executing in the one data, or it can be executing with the multiple set of data called as array of data. So based on the nature of the CPU operating on a single or multiple instruction stream and also single or multiple data stream, the Flynn, the famous scientist, he has classified systems into four categories, namely SISD, MISD, SIMD, and MIMD. See, these are the main classification of parallel computing models. So, where we have SISD, as the name implies here, it refers to single instruction, single data. That means the computer can operate only on one instruction stream and one data stream at any given instant. So, it is going to be the traditional model, whatever we follow, and it also is just simply the von Neumann computing model where we have only single CPU computer. So in this case, I think parallel processing cannot be achieved to a larger extent because it is going to operate only on single instruction and single data. It is not possible to achieve multiple processing. And now if we have the next category could be, it is like a kind of a matrix. So we fix the data stream to be one, the data stream is single, but instruction stream we move on to multiple. So we have multiple instruction and single data. I think you could wonder how come multiple instruction and single data. For example, if we can take a plus b, I think we can just see it in the board so that it will be still more clear. So this single instruction, single data, I think it's a normal computers what we follow. So the traditional von Neumann computer will come under the single instruction, single data. Here comes multiple instruction, single data. Maybe for example, we have the data x and y. So for this data x and y, we may be required to do multiple operations. We may be asked to do the addition. We have to find the subtraction of these two, or we have to find the product of these two numbers x and y. Okay, or you have to divide x by y. So like this, on the same data x and y, we might be required to do multiple operations. So if that is the case, each operation will be specified by single instruction. Okay, so we have multiple instructions but operating on the same data, single data. So this will come under the category MISD, and most of the pipeline computers can be quoted as a very good example for MISD. Okay, then comes SIMD. And actually, SIMD here, as the name implies, it refers to single instruction, multiple data. So the data is going to be more. Okay, maybe again for this, you can take an example. I have an array or array A and B. And this array is going to have 100 numbers, 100 elements. So A of 100 and B of 100. So if you want to perform addition on these two array elements, then you might be required to perform A of 0 plus B of 0. Okay, and then A of 1 plus B of 1. Like this, you might be required to add the two array elements, all the array elements. Okay, so here we have up to A of 99 plus B of 99. So I want to perform the same operation addition on different elements. Okay, so this A and B is going to be set of 100 elements. So we have vector, that is otherwise called as a vector processor. So here the data is multiple, but the instruction, the operation to be done on this multiple data is only addition. The single instruction is addition, and this addition is going to be performed on multiple data. So it comes under the category SIMD. And the other name for this could be the vector processor, and this is going to be a very good example for fine-grained data parallel computers. Okay, so the data is parallel, and the parallel in the sense that it is going to be coming under the category fine-grained. Then comes a last classification, MIMD, which is nothing but multiple instruction and multiple data. The instruction is also multiple and the data is also multiple. Might be you can combine these two together, so you might have, instead of x and y, you can have array of data, and in all these array elements you have to perform these different operations. So multiple operations also to be performed, and it has to be performed on multiple data. So that is going to be the model referred as MIMD, and all the multi-computers and the multi-processor structure, whatever we have, that may be able to support this MIMD classification. So we have discussed the parallel computing can be performed based on the Flynn's classification. So we can operate on instruction stream, and we can operate on the data stream, and this instruction stream can be single or multiple in nature, and similarly the data stream also can be single or multiple. So based on this we have four classifications: single instruction, single data; single instruction, multiple data; multiple instruction, single data; multiple instruction, multiple data. So these four classifications is very much possible, which comes under the model Flynn's model. Now we will just go back to the next topic, multiple processor organization. Maybe here we can just have the taxonomy, how the processors are going to be organized. So to start with, we have the processor organization, and as we have discussed so far, it can have four classifications, namely SISD, SIMD, MISD, and MIMD. Then the further classification of this structure could be explored like this: SISD, as the name implies, it is going to operate only on single instruction and single data. All the uniprocessor models will follow this SISD scheme. And coming to multiple data, if it is going to be multiple data, it can be identified as a vector processor or array processor. The crux of this is that it is going to operate on array of data. Then comes MIMD, where both instructions and the data are going to be multiple in nature. And if they are going to be multiple in nature, it can be further classified into two categories, namely the shared memory or distributed memory. So what we mean by shared memory and distributed memory? So we have multiple computers here, and these multiple computers can have a common single shared memory. If that is the case, it is going to be identified as a tightly coupled shared memory. Or the memory can be distributed, each processor can have their own memory, and apart from this they can also share the memory. So the distributed memory is otherwise called as a loosely coupled computers, and whereas this shared memory will come under the category tightly coupled. And again, this shared memory tightly coupled can be further classified into two categories, namely the symmetric multiprocessor and non-uniform memory access. In case of symmetric multiprocessor, all the processors are going to be homogeneous in nature, and they have the same configuration, and they are going to share the common memory, and there is a uniform memory for all the processors. So this will come under the category uniform memory access. Symmetric multiprocessor is otherwise referred as uniform memory access, whereas the other concept for this could be the non-uniform memory access, where here each processor will have their own local memory and some common memory. So if they are going to refer something from the local memory, it is going to be fastly done, whereas if they are going to access the content from the shared memory, it may take extra time. So the access time for the processor to refer to the data items available in the local memory and the data items available in the global memory are going to be non-uniform. So this is called as non-uniform memory access. So just to summarize, the classification of the computers, processor organization can be classified based on Flynn with four categories: SISD, SIMD, MISD, MIMD. Since it operates on single instruction and single data, uniprocessor can categorize this. And coming to this multiple data stream, we need more than one processor, and so it is otherwise referred as vector processor or array processor. And coming to multiple instruction and multiple data, the memory also is going to be required more in this case. Here the memory, if it is going to be shared, it is identified as shared memory. If it is distributed, one for each processor, then it is going to be distributed, and all cluster type of arrangements will come under this category. And coming to shared memory, again here the shared memory can be made as uniform access. It can have uniform memory access time with all the symmetric processor, or it may have non-uniform memory access. So this completes a discussion of this multiple processor organization. Thank you.